Welcome everybody. This is the second year community meeting. As you mentioned, the first one, we're sort of learning and getting feedback from folks in terms of topics. So today we have two topics that we're going to be discussing. One of which is Scott will give a little bit more details in terms of the architecture that IREE is using for some of their web deployment and execution, and contrast a little bit with some of the existing solutions. And followed afterwards by Ben and Benoit discussing like VMVX, macrokernels, and some of the exploration we are doing in that regard. And of course, we'll have some time at the end for questions, but also feel free to ask questions as we go. Any questions that is not answered, we can discuss further on the mailing list or enter on the forum if folks want to have a more dedicated meeting for us. We'll schedule the next one in roughly a month from now again. Okay, and with that, I'll hand it over to Scott to start us off.
Cool. Let me get my slides up. Okay, the slides look good. There we go. So, hello everyone. This is a slide deck that I adapted from another presentation talking a bit about how IREE is approaching running on the web. And because of the audience for that original talk, it kind of starts with some general information about what workflows with IREE look like, and then talks a bit about benchmarking results to kind of paint the whole picture end to end. Hopefully some of that won't be too dry or things that people already know, but more as a way to frame this particular platform within the context of how the whole project is set up. So with that, general information about the project. IREE is a toolkit for deploying ML programs on a bunch of different platforms with a bunch of different requirements. It's designed to be really flexible. It takes programs from high-level ML frameworks, JAX, PyTorch, TensorFlow, TensorFlow Lite, etc., and compiles them using import tools and then a compiler to generate target-specific code that IREE can run with a lightweight portable runtime. So we have our pretty diagram there on the right that's showing the various frameworks getting imported into MLIR, crunched through the compiler, and then deployed on various platforms, including the web, which is what this particular presentation focuses on the most. So here's what that workflow looks like step by step. Starting on the left, you have your particular program or ML model. You select whatever frameworks you want to use for that. Then you import that program using one of the import tools into a generic representation of that program in MLIR. JAX is used a bit here. If people haven't heard of it, it's a trending framework used for ML research. PyTorch, TF, and others are peers at the same level here. Then after that, IREE's compiler takes that imported program and compiles it for whatever targets you specify, generating device-specific code for all the bits of computation in those kernels, as well as all the data flow logic and other parts of the program surrounding the kernels. Then IREE's runtime is able to load those compiled programs and execute them on various platforms. So here, showing running them on the web in Chrome or Firefox, mobile browsers, etc. But you could also run Android, Linux, RISC-V, whatever there as well. General project philosophy, open source and community development. That's all of you guys, hello. We work with open standards a lot, so we try to invest in the low-level interfaces and really make those great. So trying to use the compute primitives that are close to the metal and leverage the compiler to really make the best use of those primitives, or advocate for adding more primitives where there might be gaps. IREE and the projects around it are designed to be configurable and flexible, so people can plug in things above, below, besides, all around at each level. And it's designed to be able to scale out to allow people to configure their programs in Python and configure the runtime at the embedded level and kind of everywhere in between there. So jumping into the specific example of deploying to the web, let's look at what it takes to take a JAX program and run it on web GPU and WebAssembly using this architecture. So this diagram is similar to that earlier one, but with a bit more detail at each step. We start on the left with your source program. This particular example will use JAX, but if you're using TensorFlow Lite, it's kind of a similar step there. That gets imported into MLIR. Then IREE's compiler runs its own compiler magic on that imported program. Then IREE generates both the host code and the device code for that program. If you have a ML program as kind of a graph of computations, you can think of the device code here as the kernel code for each of the nodes in that graph, for each layer in the neural network, and the host code as everything else that's needed to structure that program, connect the layers in the graph, issue those computations to devices, read back the results and return them to the user, all of that stuff. Then IREE packages both the host code and the device code together into a deployable file, which then its minimal runtime can execute. So for running on the web, the runtime is compiled using mscripten. That lets us keep the runtime written in C, and it'll compile it to JavaScript and WebAssembly that web pages can load and run. And contrasting this approach with similar frameworks for deploying ML programs, what IREE does that's unique is it generates all of this code specific to each program. So the runtime here doesn't need to know, what do you mean by device here, GPU? GPU, CPU, any target that we can generate something like assembly code for. So VMVX is kind of an interesting example that Ben will talk about later, where it's a bytecode interpreter versus generating like actual shared objects with native code. I think, yeah, do you want to ask a question on voice?
No, sorry, I was just gonna put a thumbs up, but that thing doesn't have thumbs up. Sorry, yeah, it's okay. It's like device code is like a more optimized version of something, right? Like the VMVX stuff. Yeah, okay, thanks.
Yeah, so the runtime here doesn't necessarily know how to perform matrix multiplication, although the microkernel stuff blurs that line. The runtime doesn't know fast Fourier transform. It's not a library of kernels in its most general format. All of the code for those dense math parts of the program are things that the compiler generates ahead of time for each program. So you don't need to generate a runtime build with just the ops that your program needs. The runtime starts with no ops, and each program contains the ops that it needs compiled in already. So this is an example of that in practice. This is abbreviated and condensed code for each of these. On the left here is a JAX program. At the bottom here is the actual computation for this program. So it's a little y equals mx plus b bit of math. And we have some data types with dimensions for those arguments defined at the top. Then that gets imported into MLIR using the ML program dialect. and the math shows up here in this main function with our multiply and our add with those data types. State is represented here with the globals that are mutable and global loads. We have getters and setters and other functions defined, carried all the way through from your source program too. Then further down in IREE's compilation, this is a snapshot of IREE's stream dialect. And we can see that the top part of this program here, this stream.executable, gets compiled to the actual device-specific code. So here we have the arithmetic dialect, multiply and add for that math. And those here for WebGPU generate Wigzil, the WebGPU shading language. This kind of compute shader code gets generated for that. We have the multiply and add here, as well as all the boilerplate compute shader code with invocations, work groups, all these indices and function names. If you were writing a shader code, piece of shader code yourself, GLSL or SPIR-V for Vulkan, OpenGL, etc., you'd write something kind of like this too. And then if we wanted to target WebAssembly instead, you could take that same code and compile it to this WebAssembly. We have our loop around those dimensions, and we have some vectorized load, multiply, add, store, and then a bunch of other loop indexing stuff that I've elided around that. Then for that bottom part here, that's the host code, and that gets lowered into IREE's hardware abstraction layer, the HAL dialect here. So we have our concept of hardware devices, and then a dispatch calling that that computation, execution barriers for synchronization, and then actually executing that command buffer on a device queue. Then this hardware abstraction layer goes down through a few different levels, depending on which deployment scenario you're going for. So on the web, if you're targeting WebGPU or WebAssembly, you would end up generating some VM bytecode that would call WebAssembly, that would call JavaScript, and that JavaScript would look kind of like this. This is what you would write if you were authoring against the WebGPU API yourself in JavaScript, where you'd request a device from the adapter, you'd create a command encoder, begin a compute pass. All of this is the host code that IREE generates too for that. And that can be optimized together with the device code. Then as the final step, all of that gets packaged into a flat buffer file that compresses pretty nicely and can get pretty small. This is a trivial program, so there's a bunch of overhead and padding and such in this size. Then IREE's runtime, JavaScript and WebAssembly for the web, can run that. If you're choosing WebGPU versus WebAssembly, or embedding debug information, or including some of these other optional features, then this size will change a bit. Then that whole program, using those files, loading that program, you can run on the web. I think at the last community meeting, I showed an example of something kind of like this too. If you were deploying a not general program with a trivial bit of math, you would build your own experience around this, do whatever you want with your program.
Yeah, and the binary size would go down as well. This is kind of the equivalent of shipping a REPL, versus if you were actually trying to ship ML using this, you would want to bake it all out ahead of time. Get rid of the bytecode, get rid of the VMFB, statically link it all together. And then we're talking about tens of kilobytes for the entire package.
Yep. I have a little section here talking about what else the compiler can do now that we're doing this work ahead of time. Instead of having the runtime do things, we can pre-compute them. So I don't go into too much detail here, But IREE can model memory allocation, it can model concurrency and device selection, among other things. So these are just examples of things that runtimes typically do that IREE can do ahead of time, reducing that runtime overhead, reducing that runtime binary size, and giving us more opportunities to do whole program optimization. Yeah. Okay. On the program authoring side of things, these are also things that typically runtimes will add support in maybe later on after they've initially been designed and built. So IREE is built to support dynamic shapes. There's still a few rough spots there, but in general, we support both static and dynamic data dimensions. IREE can model state internally. So if you have a streaming model where you're reading audio off of a microphone and you want your program to remember the last buffer of 2 seconds or whatever, and then use that information to make decisions, you can have the program track that state internally, so you're not having to pass that buffer in every time you're pushing samples in. You can just pass in the new data and have it remember that. And IREE supports flow control too. So if you want to branch or loop or implement a searching algorithm, come to a point in your program where you make some decision and then run some subgraph based on the result of that decision, that's all natively supported too. Then I also have some benchmark results here. A bit of a disclaimer for the web stuff in general. The WebAssembly backend is pretty new, and the web GPU backend isn't running at all yet. So these results are from Vulkan. It's a cross-platform GPU API, and we're still expanding our benchmarking suite and trying to generalize these results. So this is for transformer models, where we're comparing these language processing models on a bunch of different classes of devices. And we're mostly looking here at comparisons between these frameworks that are written in hardware-specific APIs, and then IREE using the more general Vulkan API, seeing that we're roughly in the same ballpark, or we're competitive, or in some cases, if we've really optimized a particular workload, we're able to achieve even better performance. Then these are some results on mobile GPU. These are image processing models that the hand-authored frameworks have spent a lot of time optimizing, so that there's a lot more of a high bar set by these. So TensorFlow Lite here, buffer versus texture. They have 2 different modes for operating in. IREE is just using buffers right now. There were some discussions on Discord about what it would take to support texture through the stack. But here we're on some of these workloads, we're within pretty close distance, and we have some known gaps on this particular workload that we're working through too. And regarding the web, we expect that the Vulkan performance will somewhat generalize to web GPU, as on the web that will go down to Vulkan or other hardware GPU APIs where it's implemented. So maybe we'll be 80% of that, and there will be some browser overhead, but that's kind of roughly what we're thinking we'll get once that's all running there. Yeah, thanks. Any questions on any of the stuff?
When can we have it?
When can we have it? So the web GPU stuff in particular, we're able to create devices and exercise the compiler code a little bit. It'll probably be another month or so to getting real programs running through with some results. And then once we have that running, then we'll be able to figure out benchmarking and how things are comparing. It seems like we're getting pretty close on web GPU. So that's good.
Do you have any hero cases to start with?
Hero cases. So there's certainly lots of shiny programs that we would like to be able to run. Stable Diffusion was mentioned on Discord. That would be cool. I think for this one in particular, I was looking at MobileNet v3 Small because it's a similar architecture to what the background blur in Zoom and Meet and these other programs are using. So that would be a kind of critical use case that it has been heavily optimized, as we can see by the gap there. So that would be really nice to try to prove the approach on. I expect that if we could run some of these language models, there are interesting applications on the web in particular where people are building games and other things that are using these language models to have a like choose your own adventure text thing, or a sentiment analysis, or seen some results of find in page on a web page where you could input a query and BERT would then be used to pick out the answer to that query on the web page, even if it is an exact text match. So all sorts of interesting applications there. Still, I guess, TBD for like what is the first big demo or use case that we would try to go after.
So if I understand correctly, what you're trying to, well, the end goal of all this would be to have these models running on the device, say the phone, but like very lean, small programs, right? That you have some JavaScript wrapper with some highly optimized GPU, Vulkan or OpenCL kernel, that you can match different things. So if you can speak into microphone and then, do the, hey, Google, do this, but straight in the device itself. And maybe collaborate this between applications or in the same app, say because if you run this as a web page, right, then you can only do the match on the web page that you run. You don't have access to the other tabs or apps. So would this be some form of like higher level run on the device, what we do in the cloud today, or is this like a smaller scope that you're looking at?
I think that in the end game, we want to be able to run any of the workflows that you do in the cloud on any of the devices, including web browsers. And I mean, there's a lot of ML inspired tech that is actually running in this web browser right now, for example. And I think that some of the use cases on these devices tend to be a little bit more real time, a little bit more media dominated, things of that nature. And so we kind of want to lean in there. I'd say also that one of the advantages to having more of a full compiler flow instead of a smaller, limited purpose runtime is that, there's lots of cases for online learning and personalization. Privacy is heavily implicated there. Being able to run the computation securely, on the client is important. So kind of all the stuff in that space, we're getting into the edges of things, I probably can't discuss publicly, but generally we'd like less of a barrier between the devices and their larger cousins.
It's like important to note as well for like browser applications. One of the most prolific systems within browsers is extensions, and extensions are not written in native code. You end up writing basically web code that runs on every single page. This is particularly true for like accessibility technology, and a lot of accessibility tools that particularly not ML end up leaning on like doing everything server side. And these kind of accessibility tools do need to migrate away from depending on servers to actually being on like the local device.
Excellent. Thank you.
There was a question in chat. I don't quite. Oh, there I have it. How many params are the models here? Is device memory a constraint? I don't know specifically parameter counts for like these benchmarked models, but device memory can definitely start to be a constraint, particularly on the web. Also, the download size is a constraint too, both for the runtime as well as the model parameters themselves. You don't want a person visiting from a mobile device in their web browser to all of a sudden have to download 300 megabytes just to use your web page. There are some more dedicated experiences on the web where you're doing a more application-based workflow, like here in Google Slides. I'm committing myself to working on this presentation and presenting it. Like I would be okay with wait a little bit to download something if it'll help me in that workflow. Also, if multiple pages start competing for weights and inputs on a mobile phone, it could be hard to control that.
Remember, this isn't just mobile phones. This is Chromebooks. This is thin clients. This is all of that too, many of which have real GPUs.
Yeah, and a lot of this stuff is not so much a concern for any ML framework here, but a concern for applications. So for example, the same things that Docs uses to use shared workers so that multiple tabs open will share a single worker, is the same kind of stuff that we as running in the web just fold right into. And so whatever Google Docs engineer wanted to embed IREE or any other web-based ML runtime would do the same things they're currently doing when they're embedding, the dictionaries and spell checking lookups and things like that are running in those shared workers already. So it's
right.
a browser infrastructure thing as opposed to other stuff.
Actually, I didn't know about the shared workers, so yeah, okay, that makes sense.
Generally, if your tab consumes large amounts of CPU and memory, then people just kill the tab.
Yeah.
The web is a terrifying place. They reinvented every concept of modern operating systems and called it something different and wrapped it in JavaScript.
Well, I mean, Scott, thank you. I mean, this is awesome. I'm still waiting for like the email sentiment detector to tell me, I'm being too mean. Please turn it back. It sounds awesome.
I'm waiting for the one that like backspaces as you're typing.
Fights with you.
And this needs to be a discourse plugin for sure.
Yeah, I think that's a lot of the hope here. When it's possible for tens to hundreds of kilobytes to add that stuff to pages, people building those experiences will then have a cost benefit trade-off that hopefully errs on the side of privacy, as opposed to we'll just stream this all to every single character you type to some EC2 instance and let it run something. That's a very hard thing to do today, but if we make it easy, it should hopefully be easier to do it on the web than to set up a whole serving infrastructure to do it and pay.
Yeah, there's a history in the web always of like if something consumes large amounts of resources, but everyone also wants to use it, that there's some standard couple that appear, and then websites just share the same model between them. It's like a relatively reasonable concept that'll
Google Fonts and things like that. Any kind of shared resources like that, I think, are interesting as well. If the models that end up getting used are canonical.
We should have like 3 levels of niceness on the politeness detector. First, it starts backspacing, then it disables the send button,
Right.
and then it kills your network.
Closes the tab.
Yeah. I have received your email. Send. Okay, thank you very much, Scott. I'm looking forward much to the more results and the Euro workloads. But with that, I think it also gave a nice ramp on for Ben and VMVX, which I think a lot of folks will be excited about. And some folks have seen the acronym, but don't necessarily know what it means and how it fits in with everything else. So Ben, take it away.
Let's see if the present works. Is this readable for everyone? This is just code from the repository, so I can send links afterwards if anyone wants to look more at this. So one of the VMVX as a term is kind of an umbrella at this point, and we'll probably rename and refactor some of these things. At the core, there's the concept of microkernels. Lots of ML runtimes and things like that have the idea of microkernels. The idea of a microkernel is it is kind of the innermost loop of any normal kernel you would have. For comparison, I have like X and N pack here. When you go to run one of their operators, they take some microkernel and then run a 3D loop on it. And the microkernel that they're running, it looks like a function call with some arguments and some buffers, and it writes into those. And so when we talk about microkernels, we're specifically talking about these kind of innermost kernel things. And in the IREE parlance, this is kind of the device code. This is what CodeGen is working on. It's a dense math. Doesn't perform allocations, just kind of sits and operates on buffers. Whereas in IREE, the equivalent to things like X and N packs, parallelize 3D is our dispatch. So when you see host code in IREE dispatching some kernel, this is effectively what that is. So there's nothing new here architecturally in IREE. This is what pretty much everyone does. The thing we're trying to do is make it possible to share these microkernels across a bunch of different deployment scenarios, because IREE is a toolkit for building different deployment experiences. One of those is like a fully dynamic, like Scott was showing on the web, of you want to be able to drag drop a compiled file into a web page and load the model and run it. You don't want to have to ship a compiler, tens of megabytes of compiler. You don't want to have to JIT on device while the user's waiting for their page to load. But this also applies to other situations where you might have security restrictions. So you can't ship executable code, that you can map into memory and execute. And the alternatives there then do become shipping compilers and everything to edge devices. So for those kind of dynamic situations where you can't run code or don't want to ship a compiler and all that entails, we want to be able to use well-written, efficient, platform-targeted microkernels and get all the benefits of having really well-written microkernels while not requiring either executable code that we ship or massive op libraries that need to be shipped. Most things, X and N pack is an example as it's used in TF-Lite. They ship all of the kernels by default. And those kernels are hand selected by humans based on what models people are interested in. And so you end up with a lot of really kind of bespoke kernels that are only used by a small subset of any particular models. Those are carried along and kind of inflicted on everyone. The idea here is we can ship the microkernels, the things that are actually at the core of this, where the performance is most sensitive, and then use the IREE VM to stitch those together and do basically the fusions that a normal op library using microkernels does. So that's one scenario. So again, deployment of dynamic code with untrusted, execution without needing a compiler. The other scenario we're also targeting, though, once we write these microkernels, it would be nice to reuse these for when you do ahead of time compilation. So you are, generating a static library that you're going to link into your application binary that has all the code. Using those microkernels just as if you had linked in a microkernel library and used it, or you're generating a dynamic library that you're going to ship to devices where you can actually load executable code. And this is most of IREE's CPU use cases today. And so the idea here is we have the microkernel library, we perform IREE code gen for the things we can call out to microkernels for, we swap and call out to them. We statically link them in, so we don't have to ship all of the microkernels, the linker, dead code strips, all the microkernels you don't use. And we still have the opportunity to use pure code generation for the things we don't have microkernels for, or where it's not beneficial to do so. So this is kind of a hybrid approach of what we have today, where we're almost purely using fully generated code, and just saying for the things we have microkernels for that we can easily identify, go and grab them. In both of these situations, though, the kind of key thing we're going for is that any model that comes in can run. You shouldn't have to worry about bringing a model into IREE and then getting like a, op not found, op not recognized, or, a particular build of your runtime or something can't run certain ops. The idea here is we always can convert everything. We optimistically then try to go for these microkernels, and hopefully, if we do it right, make them faster. So at the core of this, VMVX basically is this top graph with dynamic deployment, where we are actually running through the IREE VM. There's a runtime module that has the microkernels in it, and the code that the IREE compiler spits out in the VMFB that we load is VM code calling into those microkernels. But the kind of core when we talk about the microkernels is this little microkernel library, libuKernel. And so for the just to kind of demystify some of what this actually means, here's our current list of microkernels. They're fairly basic, what you would expect, element-wise operations. And then we've recently started adding things like MMT4D, which Benoit can chat about. The idea with these, though, is just like the XNN pack kernel, takes some buffers and has some arguments. It's the same thing here. These take some buffers and have some arguments. There's a particular shape of these that the structure of these where they are 2D tiled. So we can perform quite a few operations that would traditionally require a much larger set of kernels to perform. Things like broadcasting and reduction and stuff like that. By changing strides of these and offsets and stuff, we can perform quite a bit of work using these. The goal is to keep this set as small as possible. But one thing to note here is that these are all VMVX dot whatever. VMVX, as it's exposed as a module to the runtime, is just one of many. And there's no special privilege given to it except that we're actually building it right now. And so this is an extensibility point in IREE where if someone came along and had a model with a very specific, handwritten, optimized implementation of some things, they could provide that module at runtime or in their own microkernel library and link them in the same way. So today, this is what we have, and then we will add more examples of how to add your own and sprinkle them in. And all of those basic APIs just are shimmed in the runtime. This is the MMT4D, for example. It's just pulling out arguments, getting buffer pointer offsets, and then somewhere down here at the bottom, actually calling into the microkernel. And so there's really no magic here in this layer. It's just how to take calls from a dynamic runtime into the microkernel library. And that microkernel stuff does just what a microkernel library would do. If it's on ARIDGE64, call the special handwritten kernel for that, and otherwise fall back to a generic. More platforms, more implementations can be added here over time. And then the goal being the code generation that we do, even if we're targeting the CPU, can still call into this microkernel library if it wants, because there's nothing at this level that knows about the IREE VM or VMVX or anything. It is just a function that takes some buffers as parameters and does some work on it. And then just to show some example IR, hopefully to make that a little bit clear, here's a very basic example. I'll go through this really quickly just because I just want to anchor some of this on concrete things. So here's an example of a linalg MMT4D op. This came from a linalg.matmul. This is just because this is the only thing I got working last night. And so we start with that input. We perform the normal IREE separation of what is device code here, which ends up being the MMT4D op, because there's just one op, and the host code, which dispatches that. And what we do in CodeGen then is the normal tiling that CodeGen does. So nothing at this point is related to VMVX. This is just CodeGen running. And so we've tiled this at several levels. We've got it expressed in loops. If we were fusing, we would be able to, the fill and the MMT4D are fused here, but any number of ops could be in here. Any number of loops could be present because this is just code. In this case, those loops happen to go away because we've only tiled it to one level. The implication here being at runtime, when we dispatch this over some 3D grid, again, just like XNN pack is doing here with its 3D grid, each one of these invocations is basically just doing an MMT4D. And so if there weren't some bugs that we found the other night, this would mean the IREE VM, as it would run this code, is really doing the buffer setup and arrangement, and then calling out. And so there's very minimal overhead here. It's on the order of thousands of instructions, CPU instructions. What we then do as we get in, what makes this VMVX is the recognition of those linalg drops and their conversion into the VMVX dialect. So the linalg MMT4D became a VMVX MMT4D, and it properly captures all of the stride information and everything that's required to make that call. The fill is currently not recognized, and so you see that ends up as a bunch of loops around a store of a constant. This should be a memset, and we have a primitive for that, but that's not currently triggering. But it does, I think, at least in this example, why I'm not so embarrassed to show this is it does show that it's not mandatory that there are microkernels for everything. And this is what gives us that smooth kind of support surface of if IREE can ingest the code, IREE can run the code, even if this is not performant. People shouldn't have to worry when they're designing their models and experimenting whether their code will run or not. Just as if you're writing legal C, you shouldn't have to worry about whether Clang can actually accept it.
However, we do have a flag that says, danger, this is now slow pathed.
Right.
And issues warnings.
Right. Yeah, we do need that. And so as we continue down, we basically go to the flat buffer world. So this, again, there's still nothing IREE VM here. This is MLAR. And so this indexing is also terrible because of all these loops. This is a dense loop. This should be one loop. It's not. But again, the point being that if this was very complex indexing, performing transposes and indirect accesses through lookup tables and stuff, all of that would fully work here, even though there's no microkernel to do that. And finally, we lower that to, in this case, the VM. But the decision to go to the VM is the deployment scenario. In this case, we want this to be dynamically loadable and in IREE's sandboxed runtime that can load on any device. But from that same source here, we could instead fork off and continue down the normal CodeGen CPU path where we emit LVMIR and let LVM handle this. There's some differences here with vectorization and stuff, but conceptually, the thing that contains this VMVX MMT4D, if we were to lower this to LVM, would then emit the microkernel call to the MMT4D microkernel directly. And then there's no VM involved. There's no thunk layer doing all of this marshalling and stuff. And what's really nice about that then is, inlining an LTO can do some really nice stuff with that. Because the linker then is going to see both the microkernel that it's linking in, as well as all call sites of that microkernel. And so we can do some fairly aggressive dead code stripping, inlining, and constant propagation across these boundaries that are normally not possible in a larger op-based blast style library where you kind of have to assume the callers could be passing any parameters at all. And I do then also have an example of here where this was to show a fusion, and so this is a MMT4D and then a min, and we fuse that so that becomes MMT4D, and then a Linaldo generic with a min, and those all get tiled, and then we lower that down to the same form as before. Here's the fill that comes in, and then here's the min that's fused, and the key thing here is all of this code is running within a single work group. And so this is a single tile on kind of the primary grid that we're distributing across multiple threads. And the work that's being performed here on a small subset of the original tensor. And what that then gives us is all of the memory we're filling, and then we're performing the MMT4D on, and then we're performing this min on, is in cache. It's in cache on the core that's doing this work. The memory is local to this core and exclusive to this core, so there's no worry about contention from other parallel invocations of this. And so, ideally this and it broke. This min would become one single VMVX op that is a VMVX min, and wouldn't be all these loops. And so we're still going through memory when we'd be going MMT4D to min, but all of that memory is hot in cache. And so it's not as good as if you had fully, code gen this and done a full fusion, and as you're doing the matmul and writing each output, you're also performing the min. But this gives you the deployment scenarios that you can't get in those other cases, which is that the runtime doesn't need to have an MMT4D with min fusion compiled into it, as well as then the 100 other variants you might want of that, of min with max because it's actually a clamp, or min with max with mul, and a div because it's doing some fancy crap, ML crap. The final thing I wanted to show then was this is still very recent and still has some bugs to work out here with MMT4D in particular, but one of the deployment scenarios we're interested in is very, very small systems. So single core systems, generally bare metal, where the models you're running are generally at a very small scale. You're running hot word recognizers or screen brightness, auto screen brightness adjustment detectors, or things based on accelerometer input, where your activations are 4 floats. And so we now have the ability to generate kind of inlined execution. So this is VMVX inline. And what this does is it does IREE's normal compilation flow. So we still generate dispatch regions. We still perform the stream dialect stuff to kind of do scheduling of allocations and scheduling of the execution. But then instead of then continuing on and generating HAL code to create command buffers and stuff, that's it. We inline all of those. And so what was a dispatch here of this executable that itself contains this MMT4D call, we inline that, and now that dispatch becomes a function call to a function that has the outer loop. This is effectively what a dispatch is. It's, get some buffer subspans and then call the dispatch in a loop. And then that MMT4D dispatch is inlined as just another function. And so there's now the only places IREE's HAL shows up is on the ABI boundary for how you pass buffers in and out of an invocation. And everything else is just normal code. And so if you run the inliner, then the dispatch gets inlined. And so this is just basically calling the microkernel, which is up here in a loop. There's no threading. There's literally nothing but this. And again, this is another point where you could take this down to LVMIR then. It's just a program. We don't have that implemented yet, but we do have emit-C. And so if you were to lower this to the IREE VM dialect and then use emit-C, you will get textual C code out that represents this program that you can pass to your C compiler. Any weird bespoke embedded compiler toolchain will take it. And you will end up with a model that basically the only thing the IREE runtime is doing at that point is passing arguments and managing the buffer allocations. Everything else is in the program, embedded, inlined. And what these several examples hopefully show is almost all of this code path is the same, even though we're going to radically different deployment targets of fully ahead of time code gen versus dynamic, fully runtime dynamic behavior versus fully baked out, tiny system. This horrible indexing math that we do is consistent in all of them, which means if we fix it in all of them. And hopefully that's the thrust. And as it relates to VMVX and microkernels in particular, as we add microkernels, those become available in all three paths. We don't need to write different versions for all of them. And it really then, a user should, once they decide to use IREE for this kind of stuff, they don't have to worry about which platforms they can and cannot deploy for, or if they were deploying, to a Linux-based embedded system where they could, map pages and do executable stuff, and now they're going to bare metal where they're running in a restricted context or a enclave. They can still run their models. They can still hopefully run them with reasonable performance, and make those decisions. So that's hopefully an overview. VMVX as kind of the dynamic deployment scenario and runtime module. The microkernel library as the thing implementing these relatively small set of very orthogonal generalized microkernel ops. And then several different deployment scenarios of varying maturity, some of them not yet born, that hopefully make this an ecosystem actually worth contributing in. That's what I got. I don't know, Benoit, do you want to talk about MMT4D in particular?
I mean, if I may suggest, given the time check, I think the microkernels one would be very interesting. I'd rather us be able to give some proper time for it. So if Benoit, if you don't mind, let's move that to the next meeting and we can discuss it in more detail with some of the results. And if anybody has questions at the moment, I think that would be great to address.
That's a good idea, and it will be a good timing to do it the next edition.
Kojo?
Yeah, thanks. Cool, really cool presentation, Ben. Scott too. Thanks for the info. I think maybe I may have misunderstood the last part a bit when you discussed the microkernels and then the inlining. It sounded to me like the microkernels are being embedded, in the binary as function calls, but then it wasn't clear to me the link with actually inlining it, which you showed at the very end, and how that just became normal code instead of a regular function call.
Right. So that was inlining of so IREE's model through the compilers that we have this host and device code, and that allows us to separate the kind of dense math and really performance sensitive bits from the scheduling bits. And that generally today persists all the way to runtime. We have the hardware abstraction layer at runtime that can load those dispatchable executables of device code. It can go to WebGPU or Vulkan or CPUs and stuff. And then we preserve that host code for calling into the hardware abstraction layer to do things like call into Vulkan to dispatch that code, or place those dispatches in a thread pool in the case of the CPU. But in very constrained scenarios where you don't have threads and you don't have devices and all you want to do is make function calls, the inline mode basically lets us merge back the host and device concept such that there is just a single piece of code. So it's not specific to VMVX or the microkernels. It's just a place where VMVX and the microkernels can be used. Is that
Okay. Yeah, no, that I see. So that's it's somewhat orthogonal. That makes sense. And then the microkernels, like I was checking that doc you showed, are they the intention is that they're pre-compiled and just linked in for the the target system that we're running on?
Yeah, and in the runtime, dynamic runtime mode, they would be compiled into the runtime. The hope is by having a fairly small orthogonal set that sticks in the tens of kilobytes range of additional code, as opposed to several megabytes, which most runtimes end up growing to when they have those. And then in the ahead of time case, they would be linked in when we're producing the dynamic libraries that we would be, the machine code specific dynamic libraries that we would be deploying. And in that case, we dead code strip all of the microkernels you don't use. And so it effectively only links in the ones that you actually do.
Neat. Okay, cool. Yeah, this makes a lot of sense. And then the last quick question I had is, up until now, I mainly just thought of VMVX as like a CPU x86, specific library. Is that all targets at the moment, or is it intended to be like cover other platforms, like say mobile?
Yeah, it's for everything. So for web, for bare metal, any architecture that we actually implement them for. But the idea is we have generic versions of all the microkernels just written in C, and so anything that can compile C could run these. And one thing to note is that these microkernels, if you were running on a system with a DSP, the microkernels, their implementations could call out to that DSP. And so there's a blurry line there of like what is a device and what is an accelerator and stuff like that. But in the mold of if your accelerator is a function call you make to a library that runs some code inline, then things like that are kind of fit into the microkernel kind of approach, and would be useful both with full code gen to machine code or for dynamic deployment in these situations.